Good afternoon to all of you.
Good afternoon,
Good
sir.
afternoon, sir.
Good afternoon,
Good
sir.
afternoon, sir.
सर एक बार H2O का एमो डायग्राम एक बार ओपन करेंगे। एक क्वेश्चन था पापा।
अच्छा, H2 का
सर 157 पेज।
okay, just a moment. 156. This was after this one.
157।
Okay, just a moment.
हाँ
This
सर
was
ये।
yes.
हाँ
ये
सर
है
ये
एमो डायग्राम. This is the एमो
पैरा।
डायग्राम of
हाँ
the fourth.
उसके हाँ हाँ ये पेज। हाँ सर यहाँ पर जो
इसी से
हम
एक्सप्लेन होगा.
हाँ सर यहाँ पर जो है ना लास्ट में टू टू एस के साथ जो दो हाइड्रोजन बॉन्ड कर रहा है, मतलब मिक्सिंग हो रही है। वहां पर अगर लीनियर से बाइंड होगा तो ज्यादा ओवरलैप होगा ना बेन के कंपैरिजन में।
किसके कंपैरिजन में?
मतलब लीनियर
फर्स्ट
अच्छा
सेकंड थर्ड
होगा
फोर्थ
या
कितना
बेन
होगा?
अच्छा होगा? तो
बेंट
बेंटिट तो
बेंट अच्छा होगा ना. यहाँ पे बेंट अच्छा हो रहा है ना. इस वाले में बेंट पोजीशन अच्छा है. ये कंप्लीटली नॉन बॉन्डिंग था. लीनियर केस में इसका बॉन्ड फॉर्मेशन में पार्टिसिपेशन बिल्कुल नहीं हो पाता है. ठीक है.
अगर
द
टू एस
मोमेंट
पे मतलब लास्ट में जो दिखाया है।
दिस वन ना. So we have 8 electrons. So one, two, three, four. These four moving four orbitals have to be considered, right? And we find that the top one, the topmost orbital, the HOMO, is not affected by bending, but the other, the next to that, is which was previously in a non-bonded situation. This orbital is now, because the two s1s orbitals of hydrogen are coming closer, so now there is a chance of overlap occurring between these, and a bond will be so
सर
resulting in a, yes.
टू सिग्मा जी मतलब जो लास्ट में है ना वो बोल रहा था।
2 sigma g.
एकदम लास्ट में डायग्राम का एकदम लास्ट में।
नीचे वाला, हाँ.
हाँ हाँ
दिस
हाँ
वन.
ए। यहाँ
हाँ.
पर तो लीनियर ज्यादा कंस्ट्रक्टिव होगा ना बेन के
नहीं, इसको तो मैंने
कंपैरिजन
डिस्कस
में।
किया था. आई थिंक आई हैव स्पेंट टाइम ऑन दिस. लीनियर फ्रेम में आप देखिए देखिए, दो स्फीयर, मतलब आप बेंड कर रहे हैं कैंची की तरह. देखो, इफ यू ओपन अप द scissor, suppose it is possible, the two ends are very far away from each other, right? And those two ends indicate the center of the hydrogen, right? अगर कैंची, now you have a scissor and it is moving, closing, you are closing it, right? That is the situation. and पूरी तरह से क्लोज नहीं किया है, तो ये बेंट वाली सिचुएशन है. Okay. So imagine then the two corners are brought closer. If you have two spheres at the two corners of edges, that will be closer to each other. Situation दिख रहे हो? The distance. So the overlap between this hydrogen and this oneness of the two oneness orbitals are in better. The distance between them is less, and you can easily see that uh, it will have better overlap. Distance देखो, only look at the hydrogen atoms in the linear, in bent, they are closer in this case. देखो स्फीयर के बीच का डिस्टेंस, छोटे छोटे सर्कल के बीच का डिस्टेंस कम हो रहा है कि नहीं? कैन यू रियलाइज दिस?
So then in BeS to beryllium hydride, why it is not happening? That bending overlap.
What? Oh, bending.
BeS to
Oh, BeS2, na? The beryllium hydride, right? So beryllium hydride, you have four electrons to be put up. Okay, the valence shell total number of electrons is 4. So only two orbitals need to be considered from this diagram. So first one on bending, it is stabilized, but the second one is destabilized. So this is the point. The destabilization is more. You watch my video. I have pointed out two reasons for this. So the second, पिछले क्लास में मैंने ये डिस्कस किया था कि now look at this. This one is getting destabilized for two reasons. One, because the same hydrogen atoms that we were talking about constructive interference, now they are having destructive interferences because the sign has changed. Sphere, the color देखो, एक नेगेटिव है तो एक पॉजिटिव है, तो साइन ऑफ द वेव फंक्शन इज डिफरेंट. सेम बेंट कंडीशन, but the two are having opposite sign of the wave function, and so there is destructive interference between the two, more stronger destructive interference. So this will raise the energy. Okay, one. Two, look at the overlap with the p orbital. This was having greater overlap. Now in bent condition it is having poor overlap. So both the reasons, overall thing is that the increase in energy of this orbital is much more than the decrease in energy for this one. So in BH2, uh, it is, in case in this, it is better to have linear geometry. Okay, the destabilization of 1 sigma u is more than the stabilization of 2 sigma g. Okay, because of poor overlap of जो constructive interference हो रहा है वो यहाँ पे हो रहा है. See, this part, this is having negative sign, this is positive. अगर आप ऐसे देखते हैं तो यहाँ पे पॉजिटिव पॉजिटिव ओवरलैप हो रहा है, यहाँ पे नेगेटिव 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 का ओवरलैप हो रहा है, which is good, which is a constructive interference, good for them, and it is happening over a greater broad bigger region, right? The region of overlap where the constructive interference occurs is less now. Okay, so the uh, with the S and P, the interaction of S and P, the orbital overlap, that is poor. One, the destructive interference is stronger, so that is also weakening the thing. So because of both these reasons, leads to overall greater destabilization of the bent structure as compared to the stabilization of the uh, this one, the second orbital. ठीक है?
और सर वो ऐसा जे जब बेंडिंग कंडीशन में 2 सिग्मा जी के
हाँ,
बेंडिंग कंडीशन में तो हाइड्रोजन हाइड्रोजन का न्यूक्लियस तो
मतलब
मतलब
पास आएगा, लेकिन हाँ,
हाँ तो
दे विल बी क्लोज. हम कैंची पूरी तरह से बंद नहीं कर रहे हैं. The scissor is not closing completely. Scissor is partially bent condition we are talking about, right? It is not even 90-degree angle. It is more than that, around 100 something. So it is, but ठीक है, तो न्यूक्लियस तो दूर रहेगा. न्यूक्लियस, लेकिन न्यूक्लियस हम सेंटर टू सेंटर डिस्टेंस देख रहे हैं ना. Whenever you have a sphere, what I'm always telling you that you look at the center of to center distance. ठीक है? That is how we started this. No. And look at these spheres, now they are closer. मतलब एक stretched condition में पूरा bond ऐसे तो दोनों बाहर की तरफ खुल जाएगा. So you have, if you are thinking of this one, AB2 type, H2 type molecule, we generally, so I have A, so let me not give a circle, this A and H. So I was having, okay, so this is the 1s orbital that we are trying to visualize here. Okay, so this is 1s, 1s of hydrogen, AH2 type molecule. Now if it is bent, then A is in the same position, and this the same with the same length. You can imagine the circle here, imagine the circle here. So the distance, so imagine the A to be behind the plane. Imagine that these two 1s orbital sphere are coming out of the plane, so just like a scissor. So now the distance between these two has is this is a smaller distance. This was a bigger distance, right? The distance between hydrogen atoms was bigger. Now the distance between two hydrogen atoms is less. That's what I am saying. So that means the 1s orbital, the way we explained that when we formulated the G1 type group orbital, which was combination of constructive interference, so plus sign with plus sign, and this. So imagine this happening, psi A plus psi B. So this will be a better thing when the distance is less. So larger, so distance large, distance reduced. In this case, bend condition, distance is reduced. Small distance. So we are having between these two wave functions, we will be having better overlap between A and B, hydrogen A, hydrogen B, HB that we are talking about. सॉरी ये तो मैंने इसको कर दिया, तो इसको 1 2 कर है H1 और नहीं, वो भी कंफ्यूजिंग हो जाएगा, CAB BC कर देते हैं, that will be better. So the two hydrogen जो B और C है अब, so वो that is better now. Interaction is better, constructive interface, so both are in phase. The two waves interacting in phase overlap, that is constructive interference. The amplitude of the wave will increase, resultant wave, new जो wave बनेगा इलेक्ट्रॉन वेव, उसका amplitude बढ़ जाएगा, इलेक्ट्रॉन डेंसिटी बढ़ जाएगी. It is a happy situation, good for you. So this will lead to decrease in energy. यही तो बताया गया है. और दूसरे केस में क्या है कि when it is the suppose if you are making this G2 group in which you are subtracting one, so you have to remember that it was a bent condition. The same interaction which is good for constructive interference, the energy drop in this particular case. When they are having different sign, there will be destructive interference. So this is the G2 wala case which is happening here. The second one, बॉटम से पहला नहीं दूसरा, so ये destructive interference को show कर रहा है. So that is shading, the gray shading that you are seeing, that is to indicate the sign of the wave function, right? The sign of the wave function is different, and oppositely sign wave function are overlapping at a much closer distance. So it will be a strong destructive interference leading to cancellation of amplitude, and which will leave you with some zero electron density points in between. That is not a happy situation. It is leading to increase in energy between two nuclei. You are having cancellation of electron density. So that is that will increase energy of the system. And the second point was when you look at the p orbital, which was here, sorry, not this one, the p orbital which was perpendicular to the plane, it was not initially interacting, but now it is able to interact with this lobe, one of the lobes of, sorry, बहुत congested हो जा रहा है, let's rub it off. So second point was that okay, this one sorry, the interaction with the p, which is only now happening partially. Imagine in a three-dimensional frame, you will be आप 2 डायमेंशन से बाहर निकलिए, 3 डायमेंशनल में अगर आप सोचेंगे तब आपको दिखेगा कि ओवरलैप रीजन इज नाउ रिड्यूस्ड. So the because of this, what is happening here, this one is less, the overlap region is less. So the constructive which was giving you stability was this region. Okay, overlap of this orbital, which is not happening, it is less effective now. So that is how you are leading to a situation for BEF2 where BEH2 where the linear framework is good for when we are considering about water. For water, you have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So you find that this is the situation that is better. Okay, because the first one is unaffected, the top one, HOMO, is unaffected. HOMO, in case of water, HOMO is unaffected on bending, but the next to that highest occupied level, you have, if you consider, look at this, then which was, it was initially non-bonded, नॉन इंटरेक्टिव सिस्टम था, ऐसा बन गया था ये ऑर्बिटल. बेंड करने के बाद ये पी ऑर्बिटल भी पार्टिसिपेट करने लगता है. it is touching, as in picture you can see the lobes of the p orbital, that gray shade is now having overlap with the this one, hydrogen 1s orbitals, and therefore this is leading to stabilization in bent condition overall. So that's why we have bent structure in water and linear in this case. So this was the thing
और
that. हाँ जी.
सर, हाँ, जो टू टू सिग्मा जी है ना, वो क्या बॉन्डिंग कंडीशन है या नॉन बॉन्डिंग कंडीशन है वहाँ पर? क्योंकि आपने जो फोटो इलेक्ट्रॉन स्पेक्ट्रोस्कोपी का डाटा दिया था ना, वही ऑर्बिटल पोटेंशियल एनर्जी वर्सेस एटॉमिक नंबर का, तो वहाँ पर तो हाइड्रोजन एंड ऑक्सीजन का 2s का डिफरेंस तो
कौन
बहुत
सा?
ज्यादा है.
ये नॉन बॉन्डिंग है.
नहीं नहीं, एकदम नीच में मैं जो बोल रहा था, जो टू सिग्मा जी, वही
हम्म,
कंडीशन बोल रहा था. तो
ये तो
वो
बॉन्डिंग, ये तो बॉन्डिंग वाला सिचुएशन है ना.
हाँ सर, यहाँ पर तो ऑक्सीजन का 2s एंड हाइड्रोजन का टू टू मतलब 1s कॉम्बिनेशन
हम्म,
कॉम्बिनेशन किया है ना. तो
हम्म,
हाइड्रोजन का 1s और ऑक्सीजन का 2s का डिफरेंस तो बहुत ज्यादा है.
हम्म.
आपने जो
किसका?
फोटो इलेक्ट्रॉन स्पेक्ट्रोस्कोपी का डेटा दिया था वहां से, लाइक हाइड्रोजन का 1s एंड फ्लोरीन का 2s का जितना डिफरेंस है ना, उतना ही तो मतलब
उससे ज्यादा
उससे
डिफरेंस वनएस का होगा. बेरिलियम का वनएस का डिफरेंस उससे ज्यादा डिफरेंस होगा. वनएस इज लाइंग इवन लोअर देन दैट. वी आर टॉकिंग अबाउट
हाँ
बेरिलियम.
सर, यहाँ
नहीं,
ऑक्सीजन एंड
इसमें वनएस
कार्बन.
वनएस का हमने इसमें दिया कहाँ है आपको? वनएस का डेटा तो दिया नहीं है. One is lying even lower than that. 2s is here, closer to. Huh,
यस सर, हम
2s
तो
is here. हाँ.
तो ऑक्सीजन का 2s के साथ जब
नहीं,
हाइड्रोजन का
कार्बन.
1s का डिफरेंस भी तो बहुत ज्यादा है.
इसका
तो वो
बेरिलियम का, बेरिलियम कहाँ गया? बेरिलियम
नहीं,
यहाँ.
बेरिलियम बेरिलियम का नहीं है, मतलब
बेरिलियम का
वाटर का
2s
बोल
यहाँ
रहा
पे है, सॉरी. हाँ,
हूँ.
बेरिलियम का 2s
बेरिलियम का
यहाँ
हो
है.
जाएगा.
हाँ, तब.
बेरिलियम का हो जाएगा. अब मैं
हाँ,
बोल
तो
रहा
वही
हूँ
तो.
वाटर में क्या होगा क्या, क्योंकि वहां पर तो हमने बॉन्डिंग ही दिखाया है. क्योंकि ऑक्सीजन का
वाटर
2s
वाटर में
एंड
वाटर में ऑक्सीजन का टू टू एस पार्टिसिपेट कर रहा है ना.
हाँ सर,
2s.
तो बहुत डिफरेंस है ना एनर्जी का, ऑक्सीजन का 2s एंड हाइड्रोजन का 1s में.
हाँ, डिफरेंस है.
हाँ, तब
बड़ा difference
कैसे
है.
बॉन्डिंग होगा? और अगर बॉन्डिंग भी हो जाएगा तो हम
नहीं,
कैसे
इसलिए
एक्सप्लेन कर?
इसीलिए ट्राई एटॉमिक में अभी थोड़ा सा और कंसिडरेशन आएगा, जो कि बॉन्डिंग इतना तो डिफरेंस नहीं है जो हाइड्रोजन और फ्लोरीन वाले केस में था, आपका डिफरेंस बहुत ज़्यादा था। रिलेटिवली यू हैव अ लेस डिफरेंस इन केस ऑफ वाटर एंड ऑक्सीजन। ठीक है, सो 2s
और
ऑफ
सर अगर बॉन्डिंग कर भी देंगे तो हम
देखिए,
ऑक्सीजन का जो दो लोन पेयर है वो कैसे एक्सप्लेन करेंगे? क्योंकि यहाँ पर अगर एमओ से हम तो पा रहे हैं एक ही नॉन बॉन्डिंग है, एक ही नॉन बॉन्डिंग सेट है, तो हमें तो लोन पेयर के लिए दो नॉन बॉन्डिंग सेट चाहिए, नहीं तो दो लोन पेयर ऑक्सीजन का कैसे एक्सप्लेन करेंगे?
लोन
सर वो
पेयर
नॉन बॉन्डिंग ही है। एक एक मतलब ऑक्सीजन का 2s और ये ऑक्सीजन का एक
हाँ
2py
नॉन
वो
बॉन्डिंग।
नॉन बॉन्डिंग के रूप में रहता है।
एक मिनट में आपको वही तो डायग्राम दिखा रहा था वहाँ पे। सो नॉन बॉन्डिंग तो रहेगा, नॉन बॉन्डिंग जैसी सिचुएशन आएगी, दिखाते हैं। जैसे आपने सीओ में समझा, सीओ में नॉन बॉन्डिंग कैसे हम कहते हैं, relative, so you have to consider that one and then revisit H2O. So because इस तरह से आपको दो कॉम्बिनेशन आपको लेके चलना होगा, थ्री, इट इज अ लुक एट दिस। एक तो नॉन बॉन्डिंग यहाँ पे हो रहा है और दूसरा जो है नॉन बॉन्डिंग। सो इफ वी आर लुकिंग एट द एवरेजिंग ऑफ एनर्जी, इसका डिफरेंस यहाँ से बहुत कम है। ऑक्सीजन मतलब इट हैज अ ग्रेटर कंट्रीब्यूशन बिकॉज पी ऑर्बिटल ऑफ ये जो सेकेंड ऑर्बिटल है इसमें p of orbital and the 2s both are contributing here। ठीक है,
मतलब सर ये पर थ्री
ये देख,
ए वन एंड वन बी वन
and the
दो
overall thing
नॉन
is that the energy is not much different if compared with the original thing, so it has to be, both have to be treated as non-bonding। okay, in other cases you are seeing a significant drop in energy, यहाँ पे significant drop in energy है as compared to original orbitals। in this case also you have a drop, so this is a bonding situation, this is also, these are the two bonds। so if you have electrons in hydrogen atoms, sorry, in this is the G1 G2 in our system that we had discussed earlier। so four electrons, that, so total number of valence electron is 8 and we start arranging 1 2 3 4। so these two are the situations and of bonding, and this one is relatively taken to be as a non-bonding situation। See the difference from here। so it is like as the same thing, similar thing was happening when we discussed CO। CO में भी मैंने आपको बताया था, जस्ट वही कॉन्सेप्ट यहाँ पे भी लगेगा, थोड़ा ध्यान से देखेंगे तो हो जाएगा। where was that, yeah, in case of S after sp mixing, the sp mixing that happens in CO। so so this one was said to be homo, is this is a non-bonding atom, this because the combination that we worked out after, so one in which only 2s and 2p was mixing, you had, so there are situations in which this can happen। one orbital has is its energy oxygen में जो ये orbital है 2p, it has energy which is such that it can combine with 2p of carbon and 2s of carbon। so so at one point of time we consider 2p combining with 2s to form a new set of molecular orbital, so you get one this orbital and one anti-bonding orbital। In the second case we are considering combination of p of oxygen to combine with p of p orbital of the carbon। in this case here you are having a bonding MO being formed. The overall picture is somewhere in between, where both these taken together. So this is anti-bonding, this is bonding, and now we combine them together. It becomes non-bonding here, resulting in not significant change in energy as compared to the original situation. Okay, so this is, and because there are two orbitals p s, both are contributing, so it has a greater contribution from the orbitals on carbon. So carbon type orbitals are dominating it, the formation of, there is only one p orbital that is contributing from that side, and so it is this orbital is mostly having carbon like features. It is lying, most of the electron density in this orbital is lying on carbon, and it has to be taken as, it can be taken as a non-bonding orbital. Okay, so this is slightly different. You are having a molecular orbital which is such that overall picture is such that it is, the energy is not much different. Take, if I'm taking average of p and s, it is somewhere here, right? S orbital of carbon, p orbital of carbon, average energy will be lying somewhere here. The final result outcome is that this new molecular orbital is having the same energy, right? So that's why we are calling it non-bonding. Okay, so similar thing is happening over there. Just you need to analyze from this point of view. So this kind of construction of orbitals. So similar thing can be worked out for water. ठीक है ना? So वाटर के लिए और इससे आगे जाने के लिए, इसमें आप अभी से ही देख रहे हैं कि हमारा ग्रुप थ्योरी का टर्मिनोलॉजी यूज होने लगा है, इसलिए अभी हम लोग इसको थोड़ा बाद में फिर से एक बार कर सकते हैं, लेकिन आप देख सकते हैं क्लियरली ये वाला ऑर्बिटल तो नॉन बर्निंग है, क्योंकि इसको काउंटर पार्ट ही नहीं मिला ओवरलैप करने के लिए, लेकिन जिसको मिला है 2s 2pz और इधर से सिग्मा, so this is the see, it is also combining here, so 2a1, and this one is, if you combine these two orbitals, this one and this, so this one is represent the anti bonding part. ध्यान से देखिए, ठीक है? If consider two orbitals, 2s here, blue one, and this g1 or sigma that is represented here. So what will you have? One set of bonding, another anti-bonding. With respect to this one is anti-bond, something like this would be formed. Actually, we have to show two different diagrams just like that. And if you are viewing the combination of this sigma with this, then it is bonding. So taken together, bonding plus visualized from one point of view, it is giving you bonding. Another point of view, with the 2s combination, it is anti-bonding. And so overall picture should be that this is non-bonding. ठीक है?
ओके सर।
ठीक है ना? 2s को ये जो ऑर्बिटल है, G1 has suitable energy to combine with py, sorry, pz, pz orbital, and also to combine with 2s. So we start one by one. We combine one time with 2s, then we are likely to get one energy level, which will be somewhere here higher than this, and that is anti-bonding with respect to these two combinations. When we visualize sigma or G1 combining with pz, then we get at a similar position, we get an orbital which is bonding. And so when we mix them and together we visualize them together, then it is overall picture is non-bonding. So bonding in one situation, anti-bonding in another situation. So overall thing will be combination of this. So remember, that kind of situation. Yeah, like this. So one time you are combining with, it is anti-bonding with respect to one set of combination. Similar thing is happening. 2s of on oxygen, and here you are having G1 set of, or you can say sigma combination of two hydrogen, right? And the other set was having combination pz orbital, 2 pz combining. So this is the second case. So bonding in the similar at the same point, in a similar region, you are getting bonding antibody. So same. So overall picture, when we combine the things, all means are concerned, are taken care of, then it is this. Exactly same thing is happening there. ठीक है, इस तरह से आपका नॉन बॉन्डिंग आता है. Okay. So,
Okay, sir.
so actually we need to combine all the orbitals which have similar energies and similar symmetry, and then we arrive at these kind of things. So this is what it emphasizes here, emphasized over here. चलिए, ओके. सो हम कहाँ पे थे? बॉन्डिंग वाली पार्ट में, आयनिक बॉन्डिंग पे थे. वी वर डिस्कसिंग ionic bonding. So now in this framework, now we know there are two things that has to be taken care of. One was the first one was the repulsion between sorry, attraction between the ion pairs, that is negative. Interaction energy is negative, and minus ion, negatively charged ion, so overall energy is negative. And it will approach, as you approach the distance 0 between the cation and ion, the force will be infinite, the energy of interaction will also be infinite. So under those conditions, the system will collapse. So this is what the problem is, that we are visualizing this ions as point charges, plus point cation as a positive charge, and point charge with positive a point charge with positive value, uh, and a negative charge with a point charge with a negative value, that is the anion that we are visualizing. And then we are working out distance and then the closest approach. So there is some problem here. When the clouds are electron, they come very close to each other, the electron clouds will start repelling. There will be significant effect and the repulsion begins. So repulsion begins, the energy rises like this. So this is the only, if you are viewing the electron clouds at this particular distance, this is how the energy will start shooting up, increasing, positive axis. So the overall energy should be a sum of both the things, that is given by this potential well-like curve, this one. Okay. So this is the overall thing, the potential well. And remember, this potential well was also formed when in bonding. Simplest example of covalent bond, when we discussed hydrogen atom formation of hydrogen H, two hydrogen atoms approaching each other. Remember, a similar kind of profile was obtained. And there also I emphasize this part, that for a stable system in this universe, a balance of repulsion and attraction is necessary. Otherwise, it will lead to total collapse. If it is only attraction, that will lead to a total collapse of the system. Okay. So here also we are observing that similar potential, the mechanisms are different how we are arriving at this thing, but the thing is that in this case also there is a potential well, potential energy, plot of potential energy which is having a well-like pattern, we call it potential well. And at the bottom of the well, the energy is lowest. Lowest energy is here. And how do you find that energy? By if you take the differential, first differential of this, first derivative of du by dr. This gives you the energy present at that point. So that one is so we just try to work on this. So I gave you one equations to account for this repulsion between electron cloud. There was bond suggestion b by that was given, and so repulsive energy represented by er v by rn, representing that factor ec. For within the crystal you have large number of cations and anions arranged in a geometrical pattern. So taking care of that, you have this equation, this particular term. A is the Madelung constant. Now you know that what is Madelung constant. It is a converging series, mathematical series, which takes into account the geometry of the system, where the positive ions are, whether negative ions are, how many, at what distance, and then it helps you in some summation of the or all the electrostatic forces that is present between cations and anions. So this one, after when you apply, so in the equilibrium condition, when the system is having lowest possible energy, that is what we say that equilibrium condition is. And here attraction is equal to repulsion. So if you try first derivative, take the derivative, equate it to 0, replace the this is the bond coefficient, which is taken into in terms of a all other different terms. So replace this in b by rn where that was, so replace this thing is being replaced over here, original equation. So you get this term which is called Bond-Landau equation. This is the expression of energy. So this gives you the expression for energy. Q naught is the lattice energy under those conditions where repulsion is equal to attraction. So further simplification of Bond-Landau equation is that you take the terms which are constant, it is equal to 1.39, and then you have Madelung constant z plus z minus r naught and 1 minus n. So this is the bond exponent, taking into account the repulsion which is derived from the data. Further simplification was done by Kapuscinski, who observed something peculiar, that A by n ion. So as per the formula, what is the number of ion, and as per the geometry of the crystal, what is the Madelung constant? If you take the ratio, it is found to be similar, approximately the same, you can say, but not exactly same. It is similar but not same. And also that if the coordination number increases, this ratio increases. You also know that the radius of cation or anion increases as the coordination number increases. So this so if I take 1 by r, which then it is decreasing with r, so 1 by r it will decreases with coordination number. A by n ion, this is increases with coordination number, and so overall thing will be, it will remain constant, not much variation, it will remain. So taking together this A into, and this was the idea that has taken shape and got into this kind of thing, equation, where so this is A subscript, typing error is there, Na, that is Avogadro's number, z plus z minus e square. So this was the equation, which was further simplified into kappa. This is the Kapuscinski constant, and number of ions in the formula, in the formula of the compound, by r naught. R naught is the equilibrium distance, z plus z minus. So and this R star is the value where there is significant repulsion between the electron cloud. So for that thing, so it was found to be 34.5 picometers. So it is also constant, taken to be constant in case of a rock salt structure. And that's how we are analyzing everything in terms of rock salt structure, taking into account n ion number of formula unit, and the capacitance T constant is taking care of all the other factors, which is 1.21. So you have this one formula, if you know, so number of ions in the formula, and then the charges, the modulus, you're taking the modulus of this z plus z minus multiplication term, and so it becomes a little simpler. So everything can be discussed in terms of hypothetical rock salt structure. So you don't have to know all the Madelung constants. Just knowing this Kapuscinski constant and the formula of the ion compound, you can calculate the lattice energy. So and this was just to give you background. The next few following slides, that this idea many people do not understand. When I say that as the coordination number increases, the ionic radius increases. This is a very basic thing you should know from BSc, right in the BSc, because how, so for this reason that आपको ये समझना पड़ेगा कि ionic radius calculate कैसे करते हैं, how do we determine the ionic radius, and then if you realize this, then you will be able to appreciate how this thing is discussed. When I say with coordination number ionic radius increases, we have to see that when we have 4 ions such as this, look at the central ion, so they will be opposing, there will be repulsion between the surrounding ions, repulsion between surrounding ions. This is something that we have not yet considered. And when you look at it, even if the central cation is metal surrounded by, so metal, so suppose X minus is approaching metal ion, and so the situation is this: there is a metal cation, X minus ion is coming closer to it, it is feeling attraction and gets arranged around it. One, another X minus comes in, tries to approach it, and they are approaching each other closely. So we are taking into account the attraction between metal and cation and the anion. However, there will be repulsion between these two cation, repulsion between anions. So in a similar case, if I take M plus and try to arrange X minus, X minus, X minus, and analyze another case where there are 4 such things, so something like this. So what is the difference? The thing is that as soon as so in this case the repulsion, there are 2 X minus anions, so the repulsion between them will be less. The overall result will be that the metal to, they will be approach the metal ion with a much closely, metal ion के बहुत पास आ जाएंगे, ठीक है. तो metal to this distance will be shortest, ठीक है. So the distance between metal and this the R, and then you so this R plus R minus that we are talking about will be less. But as if you have more than 2 or 3, so here we have coordination number of 3 surrounding ions. So the repulsion between the X minus and this negatively charged ions will be more. So as they are, suppose they are approaching M plus ion, as they come closer, they will also feel the repulsion of the other one anion will feel the repulsion of other two anions, and they will stop at a point slightly away as compared to case 1. ये केस 1 में जैसा था उससे ज़्यादा डिस्टेंस पे वो रुक जाएंगे, ठीक है, because they are feeling the repulsion of others. Now you look at this. If there are more than 3, 4 are approaching, because they are looking at the M plus positive charge at the nucleus, at the on the metal ion. All these negatively charged ions are approaching this M plus, but as they try to come closer to the metal ion, they also experience a repulsion from these surroundings immediately, immediate ions which is surrounding it. So there are 3 such ions which will be repelling the other ions. So at some point further, the distance between M plus and X minus will increase. They will be stopping at a some equilibrium position जो आएगा वो थोड़ा सा दूरी पे आएगा. It will be slightly at a distant position as compared to the previous 2 situations. And so your center to center distance between metal cation and anion will depend on these 3 factors, the coordination number. And then because they are now separating away from the so here the mx distance is larger, will become larger. Here it is the shortest. So these are the 3 cases that I can discuss to give you an idea of what is happening. So if you have octahedral coordination, you have 6 ions surrounding it. The distance, the repulsion, each of the anion will be feeling a force of 5 other anions, right? So because of this repulsion, they will stay back. थोड़ा सा पीछे रह जाएंगे. They will come back to a certain position where the repulsion will be less. ठीक है. So मेटल आयन को अकेले में जितना पास मेटल आयन के वो जा सकते थे उतना पास नहीं जाएंगे, थोड़ा सा पीछे रह जाएंगे, ठीक है. So overall thing is that the center to center distance of cation and anion will increase, and this distance increases, the central atom, its electron cloud gets more space to adjust. So the radius that you account for the metal ion is bigger. Or in this manner you can account for any other situation, any other thing, that overall the thing is you will have, whenever there is increase in coordination number, there is always an increase in the radius of the ions. So this is the point, and this was a point which was taken care of in Kapuscinski equation, और वहां से उसने सिंप्लीफाई करना शुरू किया ऑब्जर्विंग दिस पॉइंट. Okay, so this is the basic point how ionic radius is calculated. You take oxygen as the reference point and deduct 140 picometer, assume anything like MgO like structure, and then start making a scheme. So this is how the typically ionic radius is determined. And so if you have, so observing this, you can clearly see the radius is increasing. Cesium plus sodium, maximum data points are observed. So each circle is the experimental result of performed performed by some scientists. So clearly it is the trend is consistent no matter what metal you are taking. If the coordination number increases, the ionic radius increases too. So it is to be understood in terms of because as the coordination number increases, the repulsion amongst the surrounding ions the one that we have just discussed, becomes greater and causes them to go back a bit, stay a, थोड़ा सा पीछे ही रुक जाएगा, एकदम उतना पास तक नहीं जा पाएगा जैसे नंबर ऑफ सराउंडिंग आयंस बढ़ेगा. सो इस तरह से आप सोचें, तो मेटल टू द डिस्टेंस बिटवीन द metal ion and the surrounding counter ion increases, and this electron cloud on the central ion will expand. This is what gives you. Or next thing that we were trying to discuss was polarizability. आज हमें यही से स्टार्ट करना था एक्चुअली, आज तो क्लास ही खत्म हो गई. पोलराइजेबिलिटी आप समझते हैं, व्हाट इज पोलराइजेबिलिटी एंड पोलराइजिंग पावर. So let me just introduce the terms, how it is. So suppose you have any atom, you have a electron cloud. So you have electrons distributed around that, and at the center you have nucleus, which is positively charged. Overall, the distribution of electrons is spherically symmetric. This is the isolated atom. Okay. Now, if you suppose so, what we mean by, there is a term also called polarization. Polarization का क्या मतलब होता है? Which means creating two poles. Two poles or more than two poles, maybe creating poles. So in this we are talking about electric dipole. We are talking about electric. So two poles can be called, we are creating a dipole. What kind of dipole? This is an electric field. So electric dipole. ये कैसे होगा? ये अभी तो इसमें नहीं है. Look at this. If this is the picture of an atom which has an atom which has distribution of electrons, electron densities in a spherical pattern, so spherically symmetric. So where is the center of charge? Center of positive charge, center of positive charge at the nucleus, at the center. So let me यहाँ पे draw करके देखते हैं. So center of positive charge is here. Where is the center of negative charge? अगर spherical distribution है negative charges का, where is the center of negative charge? At the center of the sphere, at the same point. So the center of, if you look at this distribution of electrons, and in this way it is spherically symmetric. Okay, so the center of positive charge, center of positive charges, that you have large number of protons and the center is nucleus, and center of negative charges both coincide. This is the case of an isolated atom. Coincide. So no separation of charges, center of positive charge, center of negative charge, both are at the same point. So there's no poles. So you cannot talk of any poles created. Okay. Now look at the other situation. The same thing is subjected to electric field. You put it under electric field and what will happen? So how can you put it under electric field? Look at this. So creating two poles is polarization. Let me just explain this point. So now what happens if you subject it to electric field? So suppose we apply an electric field in this direction. How will you apply the electric field? क्या करोगे? एक बैटरी लोगे. You take a battery, put a parallel plate, and sorry, diagram थोड़ा सा, if I can make it so. This is the negatively charged plate, and on this side I put it like this. So this is a positively charged plate, and suppose if I am putting it like this, then what will happen? Electrons will feel attracted to this plate, they will move to this side. Protons in an atom, protons are more massive, nucleus is massive, protons are heavier, positive charge, but heavy. They are heavier. Electrons, negative charges, these are lighter, less mass, that is by factor 1 by 2000 times less. ठीक है. So what will happen when the same amount of force अगर apply करेंगे, जो हल्का होगा वो ज़्यादा move करेगा. The overall result will be what? This spherically symmetric distribution of electron is no longer there. It will become something like this, distorted towards. So there is a distortion produced in the electron cloud, and now it will appear something like this. So this is, we see that now it is not spherically symmetric. The electron cloud gets distorted. So what we are seeing here, the electron cloud gets distorted, or a distortion is produced, distorted, or you can say deformed. पहले स्फेरिकली सिमेट्रिक था, स्फेरिकल जैसा, स्फीयर जैसा दिख रहा था इलेक्ट्रॉन क्लाउड का डिस्ट्रीब्यूशन. नाउ द इलेक्ट्रॉन क्लाउड हैज ये डिफॉर्म हो गया है, स्फेरिकल सिमेट्री नहीं है. Now in such situation, if you have this kind of, there is more number of electrons on this side of the nucleus, and other side it is less. ठीक है. So यहाँ पे, so what will, the center of negative charge is here, center of positive charge is here. ठीक है. So centered, so separated by a distance r, you have created a dipole. This is polarization. ठीक है. This is polarization. You have created two poles are created, one positive pole, two poles. So a dipole has been created. When you apply electric field, this is what happens to even to a neutral atom, which is neutral atom is having a positive charge of protons at the nucleus, and electrons are arranged around it in a spherical pattern. And but initially, so we have center of positive charge, center of negative charge, both are coinciding. But now we can clearly see that when electric field is applied, electrons are more mobile, electrons are more mobile, they can move easily, and so you can see that they are dislocated from their point towards the positive field. So this thing happens. Now a similar kind of electric field can also be produced by, so creation of dipole, you learned, is polarization, right? So there is distortion of the electron cloud. So we have created a dipole by, this dipole has been created by distortion of the electron cloud, number one. How was the distortion brought about? By putting an electric field. ठीक है, अब आप देखिए कि the same effect can also be brought about by putting a small charge such as lithium plus cation. If it is placed near it, the same kind of electric field can be produced. Similar type of electric field can also be produced by this. Field produced and distortion of the electron cloud occurs. So this distortion occurs, and this is also so similarly. So because this is a point small charge in a very small in a small volume, it will it will attract the electrons towards itself, and so the electrons will be moving to this side, and a similar in exactly the same fashion you have creation of two poles, positive pole and negative pole. So this is how we have arrived at, by looking at the distribution of negative charges, finding the center of that negative charge is where it is located, and is the center of negative charge coinciding with the center of positive charge. If yes, then there is no poles are created. If the 2 points are different, located by separated by a certain distance r, then yes, we have got a dipole. 2 poles are created, a positive pole, a negative pole. So ये आपका ध्रुवीकरण जिसको कहते हैं वो हो गया, पोलराइजेशन. ठीक है. So this is polarization, and how easily you can distort the electron cloud, how easily the distort cloud of an atom can be distorted. That is polarizability, the ability to undergo distortion. How easily, the ease of distortion produced is polarizability. And polarizing power is that, for like a lithium atom, it can bring about distortion in the neighboring atom. Neighboring अपने पास वाले का इलेक्ट्रॉन क्लाउड को डिस्टॉर्ट कर देना, ये पोलराइजिंग पावर है. हाउ इजीली यू कैन डिफॉर्म, उसके शेप को उल्टा पुल्टा कर दो, जो स्फेरिकल जैसा दिख रहा था इलेक्ट्रॉन क्लाउड, उसको उससे ओवल कर दो या कुछ और तरीके का कर दो. दैट इज डिफॉर्मेशन, डिस्टॉर्शन. सो ये कितनी आसानी से अपने बगल वाले के इलेक्ट्रॉन क्लाउड कर सकते हैं, वो पोलराइजिंग पावर होता है. अपना खुद का इलेक्ट्रॉन क्लाउड कितनी आसानी से डिस्टॉर्ट हो जाए, वो पोलराइजेबिलिटी कहलाता है. ठीक है. सो द ईज ऑफ, अंग्रेजी में कहेंगे तो ईज ऑफ डिस्टॉर्शन ऑफ एन इलेक्ट्रॉन क्लाउड ऑफ एन एटम इज पोलराइजेशन, polarizability. And the polarizing power is to bring about this polarization. How easily the electron you can distort the electron cloud of a neighboring atom, that is polarization. So this was the thing. ये अगर आप फंडामेंटली समझ रहे हैं तो किसी भी न्यूट्रल एटम में भी हम उसमें भी पोलराइजेशन हो सकता है, और अगर नेगेटिवली चार्ज आयन हो तब तो और भी अच्छे से होगा. ठीक है, बिकॉज द न्यूक्लियस विल नॉट बी एबल टू होल्ड all the charges under the influence of electric fields. इतना strongly सारे electrons को पकड़ नहीं पाएगा, और इस तरह से और आसानी से हो सकता है. तो this is the idea. You have spherical atom with no dipole, and how we are looking at the formation of dipole? Centers, spherically symmetric distribution of electrons. तो red color है पूरा electrons का distribution है, and center पे positive charge. So bringing a स्मॉल चार्ज सच एज लिथियम प्लस से जो हमने दिखाया आपको, उसी तरह का ऐसा कुछ होता है. तो नेगेटिव चार्ज एक तरफ और सिमेट्रिक इस पॉजिटिव चार्ज वो तो अपनी जगह पे ही रहेगा, लेकिन इलेक्ट्रॉन्स क्लाउड डिस्टॉर्ट हो जाएगा और एक डाइपोल क्रिएट होगा. सो दिस इज व्हाट इज कॉल्ड पोलराइजेशन. सो न्यूट्रल स्पीशीज, स्टार्टिंग फ्रॉम अ न्यूट्रल स्पीशीज, bring a positive charge near it, electrons will accumulate on this side, giving you center of negative charge is here, center of positive charge is here, and you have a distance. Okay, so this is a dipole is created. A dipole can also be created when you bring an ion, dipole. So this was by ion, this is induced by a dipole. But the induced dipole, so this dipole will be slightly weaker because practically it means that you are having, here we are talking about example of lithium plus a complete charge, but here we are talking about a molecule such as mm, it is partial charge. Whenever you talk of dipole that we usually create in molecules, it is only collection of partial charge, partial positive charge, partial negative charge, and this partial charge interact with this. So this influence will always be lower than that one. Okay, so that is another thing. So this is how we define polarizability. चलिए इसको फिर आगे कंटिन्यू करेंगे नेक्स्ट डे के लिए. Neutral non-polar species could be an atom, molecule, कुछ भी atom or molecule, and you can have distribution of electron cloud, presence of an electric field, the electron clouds can be distorted. The ease of this distortion is called polarizability of atom or the molecule. So distortion, so originally non-polar thing acquires a dipole moment, and this is polarization. So you can correlate it with the energy level diagram also. So whether it's a molecule or an atom, in both cases, look at these are the field energy levels, filled, and this is the represented unfilled, or you can say occupied, not unoccupied, and this is the highest occupied orbital, and this is the lowest unoccupied orbital. So this gap is, so there are two molecules, two atoms which can have orbitals have arranged in this manner. So the boundary that you find, filled orbital, and then suddenly you have a range large unfilled orbital. So these are called frontier orbitals. If it is atomic orbital, you will say atomic orbital, lowest unoccupied atomic orbital, or lowest unoccupied molecular orbital. Both, I'm in common, all of them will have energy levels, electrons will in this manner, and so you have to find the difference between highest occupied orbital and lowest unoccupied orbital, whether it's a molecule or an atom. If you find that the difference is large, the polarizability alpha is the polarizability which is, this will be small. If alpha, this separation is small, then you are going to have high polarizability. This is how related to, in other words, you can look at the ionization energy, electron affinity, and if both having high value of ionization energy, high value of electron affinity, then alpha is also high. If there is difference between, so looking at the, it is much simpler to look at the gap between topmost filled level and lowermost unfilled level, energy level. So if the difference is small, the molecule or the atom is highly polarizable, have high polarizability. So this is represented by symbol alpha, and so if something is atom or an ion, atom or ion is placed in just the way I have told you, have certain electron distribution, and you can distort it easily, readily, it is said to be highly polarizable. If you find that the nucleus is holding tightly to this, very strongly holding this its electron, the distortion is difficult, it is only slightly distorted, or it is less distorted. So if it is only little bit distorted, then you say that it is less polarizable. Okay, so it is the case between uh, so unfilled orbitals are close to the highest energy orbitals, that is highly polarizable. And such atoms, the highly polarizable ones that we are talking about, or the atoms which are having high polarizability, are found near the bottom of the periodic table. You have heavier atoms, large and heavy atoms. So you will find that they have this kind of energy separation. They have a very small separation between highest occupied orbital and lowest unoccupied orbital. The gap is less. Highest occupied orbital and lowest unoccupied orbital. So this gap is, they are close. Energy is less and they are highly polarizable. Heavier alkali metals, heavier halogens, they are most polarizable. Small light atoms such as fluorine, these are least polarizable. They have, the electron cloud is very tightly held by the nucleus. Effective nuclear charge is high, and they will be least polarizable. So this is polarizing power is the ability to distort the electron cloud of the neighboring atom. So ये दूसरे किसी पास में जो एटम है या अनायन है, उसकी क्लाउड को आप कितने आसानी से डिस्टॉर्ट कर पाते हो, दैट इज पोलराइजिंग पावर. So we say that lithium has a greater polarizing power as compared to sodium plus. Lithium plus Li plus is more polarized, having more polarizing power as compared to Na plus. That is, a lithium plus ion being small, it has high charge density, charge to volume ratio is high, and so when placed near an atom, it produces greater amount of distortion. So it has high polarizing power. ओके, सो ये चीज, अब इसका इफेक्ट क्या होगा आयनिक बॉन्डिंग में, नेक्स्ट क्लास में डिस्कस करेंगे. ठीक है, सो विल डिस्कस द नेक्स्ट क्लास हाउ दिस अफेक्ट्स योर बॉन्डिंग सिचुएशन ऑन मंडे.
थैंक यू सर.